Hey, howdy everyone. So up until now, we've talked about uncertainty. We've talked about how we build multiple realizations and scenarios to represent subsurface uncertainty. But now we're going to talk about decision making. How do we make a decision given an uncertainty model? And so fundamentally, if you think about the problem, we have provided a reasonable representation of uncertainty. We recognize that it is an uncertainty model. It's not perfect, but it's useful. And so we may have a model that tells us what's the uncertainty, or the PDF, the probability density function for the connected volume at a location if we drill at that location. It might also tell us what's the oil in place over the entire reservoir. What would we anticipate as a recovery factor if we're trying to relate exactly how does that volume in place turn into potential flow, and what can we deliver to a market, and so forth. All of these things are important to be able to impact decision making. We make a lot of important decisions with these uncertainty models. We decide on the number of wells, the locations of the wells, what volumes we're going to inject, if we're doing a water flood, if we're doing gas, tertiary recovery, if we're doing something chemical, whatever it might be, we have to make a decision. In fact, here's our challenge. We have an uncertainty model that's represented as a distribution of uncertainty, a PDF. It has a range, possible outcomes, but at the very end, we can't give that model and say, we want you to assume this volume in place from here to here, go ahead and inject a certain amount of solvent based on that. No, we have to provide one estimate that can be used for the purpose of development. We have to provide a best estimate. Now it's kind of funny because all this time we said don't do that, don't make estimates, but you'll see it's different. For the purpose of subsurface development, we will need a single value, but we're going to account for the overall uncertainty and assign that best value. So we need that value, but we need to account for the cost of over and underestimation. So let's talk a little bit more about that best value, that one estimate. So consider this: multiple realizations of some type of anomaly in the subsurface, reservoir, ore body, whatever it might be. We then have to put together a development plan. We want that development plan to be globally optimum over all of the possible representations of the subsurface, the uncertainty model. If we don't, we'll end up with L, where L is the number of models, realizations, L suboptimal models. And so we would, for this possible configuration, we'd say drill here. For this one, drill here, drill here, drill here. Now this is interesting. If we do that, we have L suboptimum representations of the decision. We can't use that. We can't say, well, we have all of these locations we thought were best to drill for each one of the possible realizations of the subsurface. Just take the centroid or the average of that in space. That would not work. In fact, what we need to do is somehow come up with a single globally optimal solution to the decision over all of these possible representations. You'll notice if you look at this single well, for none of the possible configurations of the reservoir does it look like it's the very best well. But for all of them jointly, it gives us the best result. As we will show later, it will give us the highest expected profit over all the possible uncertainties. Now, of course, this is hard to do, and we'll show some general methodologies to get at this. It's complicated. It's complicated by the fact that we have a large number of parameters when it comes to making choices, not just where to put the well, where to put the second well, how to time them relative to each other, sequence. Also, we have to be worried about in full 3 dimensions where to put the well trajectory, the well bore for the best recovery, and for reliability of drilling. There's a lot of factors that come into play. We got injectors and producers. We got all kinds of things we can do with the well completion. So that's just in the case of oil and gas. We're talking about water resources, metals, other types of minerals. There's all kinds of issues around. There's all kinds of development decisions that have to be made. So it is complicated. It's not easy. What are we going to do? What's the methodology that we're going to use in order to solve this problem? We're going to make the decision that maximizes the expected value. Pretty straightforward. We're going to calculate a bunch of different models. So we'll have M realizations and scenarios of the subsurface. This is basically M is going to be the number of scenarios times the number of realizations for each one of those. So it would have been our L times our S to get M. Okay, now we're going to say develop S development scenarios. These are not subsurface scenarios. These are development scenarios. The decisions, joint decisions we need for where we're going to put the wells, where we're going to expand the open pit, whatever the subsurface decisions are, one scenario, little s, will be a whole suite of all of those decisions, one complete developmental plan. Then what we can do is we can establish a profit metric. Is it volumetrics? Is it the average gold grade? Is it the recovery factor? What is the thing that we're trying to maximize? Now, what's interesting is that, in fact, the best way to do this is to get it all of the way to dollars. Don't stop at recovery. Include the economics and get it to actual value of the project. That's the best way to do this. Don't stop early. Then what we can do is, once we have the profit metric, we calculate the profit over all of the models, little m, realizations and scenarios, for each of the developmental scenarios. Okay, so the result is that we will have a profit for each combination of model and scenario. Then what we do is we simply calculate the expectation of profit for the scenario over all of the possible subsurface models. I put a lambda in there because it's possible that the models are not equal probable. We may want to weight them. If not, we don't need the weighting. We're just taking an average, an arithmetic average. Now what we'll have is, for each one of the developmental scenarios, we'll have the expected profit. And we can pick the developmental scenario that maximizes profit. That's the best one. That would be the one with the highest profitability. All right, so that's how we go about this whole thing around making decisions, is by making it based on maximizing the value of the subsurface. Now, there are some complexities here. Now, you could look at the distribution of uncertainty and you could say having the narrowest distribution of uncertainty is the best when it comes to decision making. What's very interesting is that, in fact, in many cases, a high degree of variability when it comes to profitability results in an upside potential. Let me give you an example. We could have an unconventional reservoir which has a long positive skew on the production or rate of production, or EUR, estimated ultimate recovery from a well, distribution. And what that means is that every once in a while you're going to drill one of those wells right out on the tail, and that well is going to have the rates we need to basically pay for the operation. It's those few boomers that'll pay off the distribution. We profit in these operations because of the wide uncertainty and because of those few wells that we can get once in a while that will have incredible rates. So now we're going to talk about how to make optimum decisions in the presence of uncertainty. Now, what's interesting is we have to make a single estimate for planning. You can't plan based on a whole range of possible outcomes. You've got to make one estimate and develop for that. So you have to make a single estimate, and so you have to determine what is your cost of over and underestimation. And this will depend too on how you see risk. Are you risk averse? Are you risk seeking? Are you comfortable with risk or not? We will review methodologies by which we can code that quantitatively and then use that to support decision making. The methodology we'll employ is called a loss function. If you need to make a decision in a presence of uncertainty, we need to work with a loss function. What a loss function does for us is it quantifies the loss or the cost due to under and overestimation. Now, it's interesting because what we may find is that in general, that they are not symmetric. In fact, if we overestimate the resources in the subsurface, we will spend too much money on the topside developing facilities. We may face penalties when it comes to being unable to deliver a product, a contractual agreement. Now, if we underestimate the resources, you might think that's just good news. We'll start drilling and we'll find out that in fact we're going to get more than we expected. But that is not the best thing. There's a cost to underestimation too. It may not be as high as overestimation, but it could result in lost opportunity. We could have produced more sooner. We may even find that in order to capture that opportunity, we have to do expensive extensions or redevelopment of our facilities to do that. And so, of course, that's not optimum either. So you can see there's a cost to over and underestimation. We develop a loss function. In general, the loss function development is going to be in the domain of those who do procurement and planning, design, finance, markets, all of those people. It will be a joint effort. Now, here's a very simple example to try to help you understand the concept of a loss function. Imagine you're going out and the weather report suggests that there's a 60% probability of rain. Now, the question you have, the decision you have to make is discrete. Do you carry an umbrella? You can't half carry an umbrella. You can't 60% carry an umbrella. You have to either carry an umbrella or not. So now what is the loss function? Well, it's going to depend on the context. So we have underestimation cost, overestimation cost. The underestimation is it rains and you don't have an umbrella. The overestimation, you carry an umbrella and there's no rain. The context, a day at the zoo. Now, I don't know about all you all who have kids, but I've spent many days at the zoo and we all know how much fun that is. It's fun with the kids, but also it's a lot of work. You're hauling around a lot of gear, especially when your kids are little. And carrying that umbrella around with you when there's no rain will just be another piece of article that you have to carry when you may already be in a situation like I was for quite a few years where I was down to zone defense because the children were grossly outnumbering the responsible adults in the group. And so that would be just a struggle. And so there's a high loss to the fact you're carrying around this umbrella. You just don't have any place to put it. But then what about getting wet at the zoo? Geez, that's uncomfortable too. You got to walk around. It's hard to get dried off. You might be stuck in the rain for a while. And so that could be high cost too. How about if you're going for an interview? If you're going for an interview, which is funny, when I interviewed for this job at the University of Texas, it rained that day and I did not have an umbrella. You're going to get a bit wet. And maybe that doesn't look good. Maybe you look disorganized. I still got the job, but anyway, it may not look good. If you carry an umbrella, maybe your potential employer will look at you and say, an organized person, prepared, and they will actually see it as valuable. And it may look somewhat distinguished to have that umbrella with you. You could use it as a bit of a walking cane or look kind of cool with it. I don't know, spin it, Charlie Chaplin, whatever it is. You may find that it's not much of a loss to carry that umbrella to the interview. And so your function will look like that. You're going to the swimming pool. Well, you're going to get wet anyway. And if you stand around in a swimming pool with an umbrella, you might feel a little bit uncool. I'm not sure if that's a cool thing to do. I don't know much about cool, but that might be uncool in your social circles. And so you have a different loss function. You can see that the context matters when it comes to a loss function. And so how do we use the loss function? It's really straightforward. It's simply a convolution. We're going to convolve the probability, the uncertainty model, I should say, G, this uncertainty model here, with the loss function right here. So we're basically going to take that function, we're going to scan it across, and we're going to calculate it for every possible estimate along this distribution. We put it here, we can estimate the expected loss given an estimate of this value right here. We move it over here, the whole thing moves over, and we calculate the expected loss at that location, there, there, there. By doing that, if we repeat that at a reasonable number of locations, we'll get a nice function like this, which is the expected loss versus the estimate that we made. It's accounting for the cost of over and underestimation. In fact, it's really cool because what you'll see, in fact, is if you move this function around, that if we estimate very low, you have a very likely chance that you have, in fact, underestimated. But maybe it leveled off and that's not so costly. If you estimate very high, there's a huge probability that you, in fact, have overestimated, and that cost of overestimation might, in fact, be quite high. And when you do the calculation, you may find that you would do better off to estimate a little bit low because of the asymmetry in the cost. This is exactly what this approach is doing, and it's solving it for a range of different estimates so we can look at the plot and pick the one that minimizes the expected loss. Now, you may be the sort of person who, when I said convolution, you might have kind of glazed over and thought, oh, this is really tough. And so what I've done is I've taken one possible estimate. I took the function that we had on the previous slide, and I have put it, and I have now worked it out by hand so you can see exactly what this convolution looks like by hand. We bin the PDF, the uncertainty distribution for the value, and we binned it into a bunch of bins like this, and for each bin we took the density, integrated over that bin, and we got a probability. So the probability be from here to here, 25%, 30%, 25%, 10%, and so forth. Then what we did is we added on some numbers here, and we said this is the loss for this, based on the loss function, for this amount of over and under estimation. Then what we did is we put the loss function at one location anchored right here. So we're saying we're making that estimate right there. So let's start right there. There's a 25% chance that we are within that bin. So we would be correct. There'd be no, within tolerance, there's no error. Well, so we have a 25% times the cost of 0. That's good. So that's no cost at all. Then if we come down here and we start working our way across, what we'll see is we have a 1% chance of severe overestimation at a cost of 200K. That's severe overestimation with our function. So we take 1%, multiply it by 200K. We got 2% chance of an overestimation that's less severe and would cost us about 125K. So 2% times that. 10% chance, now it's getting significant, of about a 75K, this point right here, overestimation. And so 10% times that, then we have a 30% chance, that's huge, of an underestimation that would cost us about 50K. This point right here, extrapolated here, about 50K in the centroid. 30% times 50K, 25% chance of this, which was about 100K, 5% for 115, 2% for 115. You see it leveled off? So going on, it doesn't get any more expensive to underestimate. For some reason or other, with the decision and so forth, there was no additional cost. An expectation is a probability weighted average. The probability for each one of these losses are these percentages right here, directly from the PDF binned up. Here's the values. We go ahead and take the summation of that. These percentages add to 100%. That will be unbiased, and we get the expected loss. That's all we had to do. We just did it by hand to demonstrate it perfectly for you so you could understand it. Now, Mohan Srivastava, and I should note here, Clayton Deutsch from University of Alberta had used this example in his notes, and as I mentioned on a previous slide, I did adapt some of this material from his lecture on decision making. He did a great job in his lecture. I learned a lot when I took his course back in grad school, and I appreciate Clayton Deutsch's generosity in sharing his slide material with his previous students and others. I know he's been quite generous. So he also used this Srivastava, Mohan Srivastava, our good friends in geostatistics, very well known, the man who actually broke the Ontario lottery scratch card. That was reported within Wired, and there was a lot of interesting news around that. Super genius person had developed this idea to demonstrate the use of a loss function on a very easy problem back in 1990. I think it was an SBE paper. Yes, the reference is down here. And so I've just basically illustrated this example here, taken the figures with acknowledgement here. Thank you very much, Mo. Awesome example. So here's the idea. We have two wells, an injector and a producer. In order to produce the oil, we need to use solvent. Now we will assume a very simple process here. Uniform sweep, there's no piping, every cubic meter of solvent equals 1 cubic meter of oil. So very simple recovery mechanism. So now what's the problem? How much connected volume do we have between this well and this well? We'll keep it as a two-dimensional problem for simplicity. We need to know what's connected because then we can make the choice of how much solvent to inject. Okay? Now what's interesting is that's uncertain. We don't know perfectly well what's going on between the wells. Mohan created 500 realizations with indicator-based simulation of the shale and sand. Clearly there's a geometric model, a geometric anisotropy here with long horizontal continuity, short vertical continuity, resulting in these shale drapes. So now we have to calculate the connected volume between the wells. If I inject here, what would be able to get over here or vice versa? And so what's very interesting is if you take this model right here and you inject here, you would see immediately that this part of the reservoir would not be accessible. It would be bypassed and you would not sweep that. This part right here, this part right here. If you go through here, you're not going to capture that, you won't capture that, you won't capture that. 500 times simulated the sand and shale, then calculate the connected volume using exactly that approach there, seeing what was in fact connected, not blocked off or baffled or barriered, blocked by barriers within the shale drapes. And if you do that, you'll find you get this distribution right here. This is the connected pore volume over the 500 realizations from Mohan's paper. Now, the mean is shown here about 87 times 10 to the 3 meters cubed. So about 87,000 meters cubed. Then there was about 89,000 meters cubed, 89.4 meters, 1,000 meters cubed for a median value, a P50, and a mode of about 92, almost 93,000 meters cubed of volume. Now, we have to give one answer for the amount of solvent to inject. We have to give one value. Even though we have this uncertainty distribution, I cannot go to the operations and say inject this much solvent between 75 to 95,000 cubic meters of solvent. That would not be possible. We have to give a single value. We have to use a loss function to make a single best estimate given the cost of over and underestimation. So this is a really nice example because the loss function is completely intuitive. What is the cost of overestimation? With our problem, the way we configured it, every cubic meter of solvent will replace a cubic meter of oil. And so it's pretty straightforward, right? If we go ahead and we inject too much solvent, we overestimate the amount of volume available, connected volume. The loss is going to be the cost of the solvent. That's how much we lose per cubic meter extra injected because it will not replace any oil. It does not result in any more production. The cost of underestimation, well, that's very interesting. We will lose the oil. Whatever cubic meters of oil were not swept will stay in place, but we will not have to spend money on the solvent. So the slope here is the cost of the oil we did not get minus the cost of the solvent that we saved money on because we did not have to buy it. So this is how we calculate the loss function. Super easy, straightforward, simple. We simplified the entire problem. I hope you can see that. That's not how it'll flow and so forth. It's more complicated, but to illustrate the point, I think it does a really good job. Okay, so if you do that, you take the loss function and you scan across estimates between 75,000 meters cubed to about 96 or so thousand meters cubed, you will find the value of the estimate of the subsurface connected volume will depend on the relative cost of solvent and oil. If you have very, very cheap solvent or very, very valuable oil, a 10-to-1 ratio, you will estimate high, about 93,000 cubic meters of connected volume. If you have expensive solvent, cheap oil, it's only a 3-to-2 ratio. You're in a situation you're going to estimate much lower, about 86,000 meters cubed, and then all these other solutions are provided right here. Now here's a good question. What would happen if the solvent and the oil had the same value? Now let's go back and look at the loss function. If they had the same value, well, we'd still have a slope over here. Overestimation would have a cost. If they have the same value though, the slope here, the same cost, the slope is equal to 0, this line would come down and be right here. There is no cost to underestimation. Now when we were making an estimate here, it says there's no cost to underestimation. Then you would estimate, keep going lower and lower and lower. In fact, you could argue, given the fact that the tails may be quite uncertain, the very best estimate at that point would be 0 volume connected, because that's the only way to guarantee that you have no chance that you've overestimated. So that works, that makes sense. If they're equal to each other, there's no reason to inject a product, to spend the money operating to inject it, to get back something equally valuable to it. That would be just silly. Well, so that was an illustration of the use of a loss function to make a discrete decision. It showed why we have to make discrete decisions given an uncertainty model in the subsurface. What I've done and I put on GitHub is on GitHub I have a directory where I have a whole bunch of different Excel numerical demos. And so there is a demo available if you're interested, where you're able to change the uncertainty distribution. And then you're able to come over here and change the slopes, and you can go ahead and calculate and see how the uncertainty model will update given a variety of different costs of under and over estimation. And so this is quite powerful. This can be used if you want to try to understand kind of in a hands-on manner the concept of decision-making in the presence of uncertainty with a very simple loss function like this one shown right here. It's all linear, it's all very simple, but you can work it out in Excel. It's on my GitHub account, Geostats Guy, Excel Numerical Demos, and it was called I'll show it one more time, Decision-Making with Loss Function Demo. Quite straightforward. So if you want to try that out, there's a link right here, right to it. If you want to go ahead and just type that in, you could use it. I also have on GitHub a list of all my resources online. They have live links. You can link to everything and you can try things out. I haven't coded up in Python. I should. That'd be kind of fun. Make some graphics, make it interactive. That'd be cool. I haven't done that for a while. Okay, anyway. So that was decision making in the presence of uncertainty, specifically with some philosophical statements and concepts around that. Defense for the fact that at the end of the day, we really do need to make a single estimate in order to operate on. And then we used the loss functions. We went through the example from Mohan. I want to credit Clayton Deutsch for a lot of concepts that I borrowed within these slides from his previous course that I took. And I do appreciate his generosity with his slides and with his materials. All right. So that's it. I hope that this was useful, as usual. And I'm Michael Perch. I'm Associate Professor at the University of Texas at Austin. I am Geostats Guy on Twitter, YouTube, and GitHub, where I put out a lot of resources. All my lectures are recorded for anyone who's interested to attend and to hear about what I teach within my classes. I believe in outreach and professional development, and I hope I'm hearing that there's a lot of people in industry and elsewhere outside my classes are making good use of these courses, and that makes me very happy to hear that. So I'm always happy to discuss. All right, take care.